Shalom lekulam. So today we continue with the Hopfield model. Just like to remind you where we are. So we wrote down the Hopfield model equations and studied or analyzed. We were interested in characterizing the fixed points of the model. Now this is difficult, so we said, okay, let's start with studying it in the limit of beta going to infinity. And we did that, and we found that if there aren't too many memory patterns, then these memory patterns are fixed points of the dynamics. But there were still several open questions. One was about the stability of these fixed points. This was one question. And a second question related to the issue of associativity of the memories. So one requirement from a memory pattern that it will be associative. The idea is that if I present to you I don't know, half of myself, okay, I'm hiding, you can still see something, you can still reconstruct me using the partial image. And this is something that we were unable, or we did not analyze in the case of beta that goes to infinity in this case. The only thing that we're looking for is the question whether the memory patterns are fixed point. We were not interested in the question of whether these memory patterns are associative. In fact, to construct a network in which memory patterns are fixed points is something that is very easy to do. Have any idea how? How can I construct a network such that any memory pattern will be a fixed point of the dynamics? Let's say that this is my network, and I'm going to consider this connectivity matrix. Yeah, neurons are isolated, and the only connection that we're considering is self-connection of the neurons. We already know that these neurons, if the connectivity is strong enough, these neurons will be bistable, right? And if in the limit of large beta, and thinking about the activation function, which is hyperbolic tangent, these neurons would be plus or minus. Each neuron can attain the value of the fixed point for each neuron is plus or minus 1. These are stable fixed points. So any memory pattern is a stable fixed point of this network, right? So what's the capacity of the network? I don't know, infinite or 2 to the power of n, because any memory pattern will be a fixed point. But this is not what we mean when we talk about memory patterns, right? It's not sufficient that the network will freeze in any state. We want it to freeze only in those states that we define as memory patterns. So the fact that we were able to show that memory patterns are fixed points of the dynamics when we started the Hopfield model, this is not sufficient. We want to show that these are the fixed points and only these, or a small number of additional fixed points, not that any pattern is a fixed point. Okay, so we stopped working on this limit of beta going to infinity, and then we said, let's consider the dynamics. And to make our lives simpler, we started by considering the case of one embedded memory pattern. And we defined a global variable, this overlap variable. And in that case, we were able to show that the memory is associative, because we had the dynamics was such m dot was equal to minus m plus hyperbolic tangent of beta m, and this was m1. And when writing this equation and analyzing the fixed points of this equation, what we learned was that the first memory the only memory pattern is a fixed point of the dynamics, or something that has a large overlap with this memory pattern is a fixed point of the dynamics. And more generally, in this case of P being equal to 1, the dynamics of the network is characterized, if beta is larger than 1, the dynamics of the network is characterized by two stable fixed points, one with a positive m and one with a negative m, one with a positive overlap with this memory pattern, one with a negative overlap with this pattern, and that's it. So this is not this case. It's not that every pattern is a fixed point. Only patterns that have something to do with the first memory pattern. And then we moved on and discussed the case of P being equal to 3. And here things were more interesting. So first we found that memory patterns, or positive overlap with each of the memory patterns, were fixed points, or were stable fixed points of the dynamics, again in the case of beta larger than 1. So we have the associativity of the memory, because we were able to show that if you start close to a memory pattern, you will converge to this memory pattern. Again, not exactly to the memory pattern, because the memory patterns are binary, and here we have numbers that will not be plus or minus 1, but you will converge to something that is similar to the memory pattern. However, we also found, in this case of P being equal to 3, we found spurious memories. These memories were a weird combination of the particular of these three memories. For example, a majority rule, a state in which a neuron has a positive, the activity of a neuron is equal to the majority of the three memory patterns, was a fixed point in the limit of beta going to infinity, is a fixed point of the dynamics, and the dynamics will converge, at least in the limit of large beta, it will converge to this fixed point, because we studied the stability. Having these differential equations, we can study the dynamics, and we were able to show that these spurious states, these combined memories, are also fixed points of the dynamics. But this was only true, we were able to prove it only in the limit of beta going to infinity. And then we said, okay, let's consider a different. So if beta is smaller than 1, then we know that the network has only one fixed point. Which fixed point? 0 fixed point. So we said, let's consider the limit in which beta is larger than 1, but not much larger than 1. So the limit of beta that is close to 1. And the reason that we want to consider this limit is, well, because here we will be able to do something analytically. Questions so far? Okay, so let's write the relevant equations. So we had the fixed point equation, and the fixed point equation was M is, actually we can write them here because we don't need it. So one equation that we had was M is equal to 1 over 4 of hyperbolic tangent of beta of 3 beta M plus hyperbolic tangent of beta M. This was one equation that we wrote. And second, we have the stability matrix, which for historical reasons is also denoted by M, this time capital M, is a 3 by 3 matrix that we wrote as ABB, BAB, and BBA, where A is equal to the derivative of mi dot with respect to mi, and B is equal to the derivative of mi dot with respect to mj when I is not equal to j. And at the fixed point, we had an equation for A, which is equal to -1 plus beta over 4 times 4 minus hyperbolic tangent square of 3 beta M minus 3 hyperbolic tangent square of beta M, and B is equal to minus beta over 4 of hyperbolic tangent square of 3 beta M minus hyperbolic tangent square of beta M. So these are the things that we derived. These are the things that we derived last week. So again, we were able to compute the stability of this matrix in the limit of beta going to infinity, and we showed that this matrix, or that this fixed point, is stable. And now I'm going to study the stability of this matrix in the limit of beta, which is slightly larger than 1. And the result will be that this fixed point, this spurious fixed point that corresponds to the combination of memory patterns, is in fact unstable when beta is relatively small. So we know that it is stable when beta is large, and it will be unstable when beta is small, but still beta larger than 1. So the fixed point will be unstable. So there are two reasons why I'm teaching you this. One is we're interested in understanding the effect of beta, of this nonlinearity on the space of solutions to this model. This is one reason. And the second reason why I'm teaching you this is because I want to teach you a rather useful technique for studying these questions, studying nonlinear functions near a bifurcation point. So that's the second motivation to do this calculation. Questions? Why is it a difficult problem in the first place? Why do we need to study it in different limits rather than just plug everything in and do the calculation? So, and if I give you the numbers, A and B, then it will be trivial to compute the stability. So in principle, for any value of beta, you should be able to compute these values of A and B. The way to do it would be to find the fixed point solution and just to plug it in. So numerically, this is, so how are you going to do it numerically? Well, first you need to solve this equation. Unfortunately, you have m both here and here. So there's no explicit term for m. So you need to numerically solve this equation, and then plug the solution here, and then compute the stability. We already know that this matrix has what are the eigenvalues and eigenvectors of this matrix. There's a homogeneous direction, which would be A with the eigenvalue A plus B. And there is a heterogeneous direction, which would be 1, minus 1, 0, something like that, and with the eigenvalue of A minus B. Actually, we said A plus 2B. A plus 2B. Okay. So in general, if we want to study the stability of this matrix in general, then this is the only way that we can address it. We need to solve it this equation numerically and plug it in. But when beta is close to 1, we can actually study it analytically. So how are we going to do that? So when beta is equal to 1, let's say when beta is smaller than 1, what is the fixed point? When beta is smaller than 1, the dynamics is only single fixed point, which is m is equal to 0. Right? Now, if we look at the solution as a function of beta, so it will look something like, so this is 1, this is beta, and looking at this equation, there will be m. So until 1, there's only one solution. And then there is there's a bifurcation, pitchfork bifurcation here. So the way to solve this problem would be to look at this equation and to expand it around small m. Take leading orders of m, because we know that near the bifurcation point, m will be small. In the limit of beta going to 1, m will be equal to 0. So we can expand this equation, taking only leading terms in m. So what's the Taylor? So we all know that the hyperbolic tangent x, if we take if we expand it, it is equal. First order term is equal to x, and then the second order term is 0, and the third order term is minus x cubed. So this is when we Taylor expand hyperbolic tangent around x being equal to 0. So we can take this equation and do exactly the same thing. So let's see let's see how the solution would look like. So expanding this fixed point equation. So I'm expanding the fixed point equation. So the left-hand side of the equation is equal to m, and this will be equal to 1 over 4 hyperbolic tangent of 3 beta m. So this would give me 3 beta m minus 1 over 3 times 3 beta m cube. This is expanding this term, plus beta m minus 1 over 3 beta m beta m cube. So this is equal to beta m from these terms, and here we have minus 9 I might have a mistake in my notes, so this should be minus 9 sorry, 27. This would be minus 27, 28 over 12. So 28 over 12 is 7 over 3 beta cube m cube. O beta minus 1 m is asymptotically equal to 7 over 3 beta cube m cube. So there are 3 solutions. This is a fixed point solution. One, we see the 0 solution as before, but we are not interested in this solution. We're interested in the non-zero solution, which is beta minus 1 is asymptotically equal to 7 over 3 beta cubed m squared. So two things are worthwhile note. Well, one thing is worthwhile noting is that what is the bifurcation parameter here in this problem for those who took Lotem's course? The bifurcation parameter is a small parameter, beta minus 1, and m is proportional to square root of beta minus 1. So this is a property of the pitchfork bifurcation. So this is something we could have predicted previously. So why not take? Why did we take third order term? Why not take only first order term? Then we will only get the 0. Why not add the fifth order term? Because these would just be corrections, which would be negligible. We will have like m to the power of 4 terms. So this would be the dominant term. So we took the dominant terms, and now we have an expression. I will leave it as it's written here, but we have an expression, an analytical expression of dependence of m on beta near the fixed point. Now we can do the same trick here. Now that we have an expression for m, we can plug it in here and have analytical expressions for a and b. But again, since we are only interested in, or we're interested in the solution for small m near the bifurcation point, we can also expand these equations. So let's expand A. So A is equal to what? It's equal to -1 plus beta minus, so which term should we take here? What should we do with this term? So what will be the leading order terms here? So if hyperbolic tangent x is equal to x minus x cubed over 3, so the first order term would be x squared. And then we'll have higher order terms like x to the power of 4 from the square and x to the power of 6. So we'll just take the first order term. The first order term would be, so we have this. So we have beta over 4 times minus 3 beta m squared minus 3 times beta m squared. So this is equal to beta minus 1 minus 3 beta cube m squared. So here we have 9, 3, 12 divided by 4. So that's the first, that's a term for A. And we can do the same thing for B. So B is equal to minus beta over 4 times 3 beta m squared minus beta m squared. So this is simply equal to minus 2 beta cube m squared. This is asymptotically equal. Now the eigenvalue in the heterogeneous direction is equal to A minus B. Which is equal to beta, asymptotically equal to beta minus 1 minus beta cubed m squared. Now we know that beta minus 1 is approximately equal to 7 over 3. Beta cube m squared. So this would be equal to 7 over 3 minus 1 times beta cubed m square. This is larger than 0. So the fixed point, although this fixed point of spurious memory states, this fixed point exists, it is unstable. So the implications are, for this specific case of three memory patterns, is that when beta is sufficiently large, all memory states are fixed points, or stable fixed points, but also the spurious states of combined memory states are also stable fixed points. If beta is smaller than 1, then there's only one fixed point of the dynamics, which is m is equal to 0. If beta is larger than 1 but not too large, then the spurious memory states are fixed points but are unstable fixed points. And only the memory states and minus the memory states are fixed points of the dynamics. And it turns out that this conclusion holds also when we consider a larger number of memory states. So if we consider now the full Hopfield model in the limit of beta going to infinity, we already know, and let's say that we are below the capacity, so we know that memories and minus the memories are stable fixed points of the dynamics. But also, all combinations of an odd number of memories, all these are also fixed points. And there are many more spurious memory states than the real memory states, or those memories that we embedded in the network. Now, as we decrease beta, more and more of these spurious memory states will disappear, starting with the memory, with the spurious states that were constructed using a large number of memory patterns, and as the number of and ending with those spurious states composed of three memory patterns. So this result is actually rather general. Questions? Okay, so if we don't have questions, I would like to summarize and generalize the Hopfield model. So the Hopfield model is, I find it remarkable because I still remember the wow feeling when I first encountered the Hopfield model. The idea that you can store a large number of memory patterns in the same network in a way that is completely distributed. No single synapse is responsible to no single memory. And it turns out that this memory is very stable to many different things that you can do with it. I think it's remarkable. But there are issues, and some of these issues are easy to solve, and some of these issues with this model are more difficult to solve. So one thing that we already discussed is the case of sparse representations. So the standard Hopfield model, as it's written, fails miserably if you have if the proportion of plus ones and minus ones in the memory patterns, if this proportion is different from 1/2. We discussed solutions to this problem using a covariance rule in which we subtract the average. This is a solution to this problem. And when we use this solution, we were able to show that we can also store a large number of sparse memories in this network. I cannot tell you that I'm enthusiastic about this solution, because this solution requires fine-tuning. It requires that we will subtract really the mean and not approximately the mean. So there are many ways where one can think about removing the mean. One of them is adaptation, but usually they are not precise. And in order for the model to work, it needs to be precise. Another issue that is worthwhile, another problem with the Hopfield model is the issue of correlated memory patterns. So the memory patterns that we discussed were plus and minus 1 with a probability 1/2, independent. If we think about, let's say, visual memories, I'm looking at this brain and I'm impressed by it and I memorize it. It has a structure in it. So these two pixels that are nearby have the same color. And these two pixels that are nearby have the same color. So thinking about it from the point of view of representation in the brain, this would imply that real memory patterns have a structure in them. They are not completely random. There are various ways of addressing this this problem, and what people typically do, they somehow decorrelate the memory patterns before they are embedded in the network. So this solution, this problem has a solution, and it could be that in the brain, at least in high cortical regions, indeed memories are somewhat or representations are somewhat decorrelated. If we talk about even place cells in the hippocampus, to a first approximation, nearby points are not represented by nearby neurons. Again, this is true to a first approximation. This is not generally true even there. There is another issue which is a serious issue with the Hopfield model, which has to do with the fact that we assume that our memories have a large number of states. So how many states are there? How many possible states a synapse can attain in the Hopfield model? God forbid, no. So the Jij sum of 1 over n, sum over mu of pi mu, pj mu. For how many states? How many states? Well, this product can be either +1 or -1. So you can imagine a case that for all memory patterns this is -1, and then this would be -p over n. Or we can imagine that all of these are +1, and then this would be +p over n. So altogether, we have an order p number of possible states that the synapse can attain here. Now, if p is large, this implies that the synapse is effectively continuous. So the number of possible states that the synapse attains in this model is almost infinite. And if we relax this assumption, then horrible things happen, and this we will discuss shortly. The last point, which I'm intrigued by it, I have been intrigued by it for ever since I learned about the Hopfield model, and this is, I think, a serious issue for the Hopfield model and perhaps a serious issue in general for computational neuroscience. So what's the evidence for Hopfield-like associative memory in the brain? So what kind of, if you could have measured from every neuron and every synapse in the brain, how would you characterize the predictions of this model? How are we going to test it experimentally? So there is the naive way of testing this model. For example, the model tells us that the activation function of neurons is hyperbolic tangent. So it is sufficient that we will do measurement in the brain and find that a FI curve of cortical neurons is not hyperbolic tangent to rule out this model, right? Well, not exactly, because it's a model. We don't, when writing g of x as hyperbolic tangent of beta x or 1 plus hyperbolic tangent of beta x, we don't really mean that each and every neuron, or that even any neuron in the brain, is exactly hyperbolic tangent neuron. This is an approximation. What we have in mind is that this is an approximation that enables us to solve the model, and we think that if we make small changes to the model, this will have only a small effect on the global behavior. So the fact that neurons in the brain are not hyperbolic tangent neurons, this should not be a serious issue for the Hopfield model. Okay, so what will be a serious issue for the Hopfield model? What are the true predictions of the Hopfield model? And again, I'm asking you this question. Ignore the issue of technicalities. Let's assume that you can measure whatever you want. You're measuring from behaving humans, intracellularly, from all neurons. Do whatever you want. No ethical issues, no technological issues. So what would be the predictions of this model? What do you mean by?
It can go close to, if we're talking about the N, or similarities to one memory pattern.
Yeah.
If we're saying that they are stable, then if it's near it, it has to go to it and can't go to another memory pattern it's further from it.
So I will rephrase what you are suggesting. I will use perhaps a more mathematical language. So what you are arguing is that the signature of a Hopfield model would be attractors. The idea that if you start near a solution, you will converge to this solution. So the idea is that there are attractors in the brain. So this is an example of perhaps a global prediction of the Hopfield model. It's not unique to this model. Okay, so the question, so perhaps rephrasing what you're saying is, what's the alternatives? What are the alternative models for memory? Now, if we have an alternative model, then we can compare them with respect to the predictions. And it turns out that there aren't good alternatives. So in that sense, the Hopfield model is a winner. I don't know of any reasonable alternative. One alternative is one, at least conceptually. So in the Hopfield model, this issue of pattern completion is done using attractors. One can imagine an alternative model, which is a feed-forward model, so rather than, so this is the input layer, this is the output layer, and we need a mechanism that maintains memory in this output layer. So an alternative model would be that the issue of pattern completion or the associative nature of the model is attained using a feed-forward model. In fact, there are variants of the Hopfield model where when we talk about Jij, rather than thinking about, so this would be the feed-forward model, and the classical Hopfield model will be a recurrent network model. So the difference between this model and this model is that this is a recurrent network model and this is a feed-forward model. And the idea, it turns out that we can construct a homologue of the Hopfield model in a feed-forward manner. The idea would be that here Jij is a product of activity is given by this equation. What we will have here is that Jij would be the connectivity from neuron I here to neuron J here. That would be the idea, and this would be and this would be copied throughout the network. So the idea is that this model is like unwrapping this model in time. So thinking about the neural activity in the next time step as a neural activity in the next layer. So this would be kind of an alternative to the Hopfield model. What we will still need is some mechanism to maintain activity in the absence of input. So we know, if you remember the Simpsons neuron, that there is activity even in the absence of external input that is maintained, reverberating activity. So this would be difficult to construct using a feed-forward model, but we can think about a single cell mechanism that are just important for maintaining the activity of this particular neuron in time as a way of maintaining activity over time, and the selectivity and the associativity we can imagine that they are done in a feed-forward manner. So this would be like a competing model, but in many aspects it's very similar. So the building blocks of the Hopfield model, well, there's a lot of evidence in support for them. We know, I mean, we discussed it. There is evidence relating synapses to memory. We know that LTP or Hebbian-like plasticity is something that we see in the brain. There are even experiments. There's one experiment that was done by Susumu Tonagawa about a decade ago. What he did was to block in a very selective way NMDA receptors in area CA1 of the hippocampus. This is the area where you have a lot of recurrent connectivity. And he argued, not very convincingly, but it was convincing enough to go to science. He argued that the memories are maintained, but not the associative aspect of the memory. So animals remember, but they don't. If you present the exact stimulus, they are able to respond to it, but they are not able to generalize or to the associative aspect of the memory is gone. Questions? So what we will do now, we will take a 15-minute break, so we convene at 5 past. And then I will discuss the case where synapses are not continuous, where we have limitations on the synapses. This is important both as a continuation of the Hopfield model, but also as a way of introducing the idea of Markov chains. So this is after the break. לא, אתה לומד את ה-GIJ. אבל כל פעם שאתה רואה משהו, אתה צריך לזכור, יש לך שינוי דלטה GIJ שווה לך KN, PIMU,
פי חדש סתימה כאילו?
אתה מסתכל עליי, אתה זוכר אותי, אוקיי? יש לך איזה תבנית שיוצרת, אתה רואה אותי, אז זה יוצר תבנית פעילות במוח, ושינויים בחזקים מהמזוגות של תאים נעשות בפרופורציה למכפלה של הפעילות הפעילות.
C'est défini comme étant qu'un paramètre d'ordre en fait. Comme étant le...
אבל ראינו שתמיד כאילו... זה מה שקשור, כמות הלכטרונים שקשור לכמות מלגונים, תמיד יש לי כמות, לא יודע, 1000 זיכרונות, תמיד קיימים כאילו, תמיד, לי הם כאילו לא, נכון, זה היה פרופורציונלי, זה היה קשור ל-N, הכמות זיכרונות שיש.
לא, יש לך איזשהו כמות זיכרונות במוח, ואז אתה מוסיף את התוספת הזאת. מוסיף את התוספת הזאת. אתה יכול לחשוב על מודלים אחרים שבהם אתה שוכח, אתה כל הזמן שכחה של הדברים הישנים. אז אתה מקבל שזה זיכרונות חדשים יותר חזקים מהישנים, כל מיני תוספות שאתה יכול להכניס.
En gros, est-ce que la performance du système, tu vois que en gros, M c'est vecteur performance, et tu vois que tu as une rupture de symétrie quand bêta est inférieur à 1, M en moyenne est égal à, c'est une moyenne, donc ça vaut 0, et donc tu retiens pas, tu peux pas retenir tous tes patterns, et puis quand bêta est supérieur à sa valeur critique de 1, sometimes the input is only considered between neighboring neurons, or
this connectivity is all-to-all.
yes, well, and
It can be sparse, but the dimensionality has to be high.
okay, so in the limit of large n.
No, the question is dimensionality of the input, to understand it, of the connectivity, to understand it correctly. It's not a short range. It will not work with short range.
Okay, yeah.
If this is your question.
Yes. Yes, it was a general
It
question.
can be sparse, but it cannot be short range.
Okay. Okay.
Still, the rank of the connectivity is low. So, the matrix J is equal to 1 over n. Sum over mu, p mu transpose. So p is approximately orthogonal. So you can think of the subspace that is spanned by these vectors. Now this, if the total number of neurons is smaller, much smaller than the size of the network, then this subspaces, the rank of this matrix, J matrix, is much smaller than n. But still, it's a long, we assume long range.
Yeah. כן, כן, זהו, תרגילים טובים במובן הזה. כאילו זה נורא ארוך כזה, אבל...
שם את הקוד בסוף, ואתה זה ותצטרך...
שם את הקוד? אוקיי, אני לא שם.
הוא לא אומר לך?
לא, לא אכפת לו.
וואלה.
לא חושב שהוא עובר על הקוד.
לא, ברור לי שהוא
עובר
לא
על
עובר על
דף
הקוד, אבל אני חשבתי
שחייבים,
שהוא
כאילו,
שיש.
שיש קוד. מקווה שהוא שם עליו. אם הוא ירצה, אני אשלח לו. הוא לא העיר לי את זה, אבל לא, אבל כן, תרגילים טובים במובן הזה שקודזים. טוב, אבל זה המון עבודה. כאילו זה לא מפתיע. לא, אבל מנסה להקדיש מינימום זמן לקורסים נקודה. כאילו, קצת של זמן מחקר, ואני עובד בקשר, כן. אוקיי, זה לא קשור. יש מוטיבציה של מדענים, מההתחלה יש מוטיבציה שעובדת עם...
איך אתה יודעת כאן שלו?
קצת קשור אולי, לא למשל כן. לא, כי אני באמת חוקר לפעמים כאלה שיטות, שיטות אקראיות, דברים כאלה שסמכתי משהו. אבל הזה, הוא מאוד יומי, יש כזה. יש להם משרדים, אני לא עושה את זה, אבל לא, סתם, יש להם משימות חבר'ה של כזה. מי שמע עליהם? כמה מהסוכני חלל בחו"ל שמע עליהם? אבל לא מעט. תראי, אין ממש כסף, זה תחת משרד המדע. ומקצים כסף מספיק כדי באמת לשים שימת מדע כללי. זה עשרות מיליונים של דולרים לכל משימה. אין כסף אחר. אבל הקהילה ירצה לשלם למדינות שקשורות למדע כללי.
ואתה עובד בירושלים?
לא, זה ליד שדה התעופה.
לא, כי העבודה פה לא בסדר.
אנחנו לא בירושלים.
אתה גר?
עכשיו אני גם בשדה התעופה.
יש מלא דברים ללמוד בירושלים, או שאתה לא יכול?
כן, אני לא יכול, אני פשוט ממשיך להרצאה.
אבל מה שאני עושה, כל החברים שלי שהתחילו בשיעורים, לא מספק אותם.
לא עובד? אבל טוב. אוקיי.
יש בירושלים, נגיד,
המכון לסטטיסטיקה, המכון איך זה נקרא? לבן.
הרציונליות. הרציונליות, לא?
לא עובדים שם, לא?
אז מה מוכן לי?
מה?
אמרו לי פעם קצת למכון לרציונליות. זה ממש מצחיק אותי.
שזה נקרא רציונליות.
כן, אני יושב על המכון לרציונליות.
כן. אוקיי. אוקיי, אז הם רצו ולא רצו.
לא, ממה שאתה אנחנו שותים בצהריים. איך
אז כן.
זה של המכוניות
של מובילאיי?
כן, שם נגיד?
צריך? אוקיי, כנראה שכן. אז שם יש. זה כזה נקודתי כזה בביזואל. אני יודע. זה ביזואל כזה. אוקיי, אבל יש לי הייתי אז, יכול להיות שהייתי מנסה גם.
Okay, so the problem that we are now going to address is, this is taken from a paper that was published about a decade ago by Stefano Fusi and Larry Abbott, Nature Neuroscience paper. It's called Limits on the Memory Storage Capacity of Bounded Synapses. The first ideas or hints about this problem started in somewhere in the 1990s. when Stefano Fusi was, I think, a graduate student of the late Daniel Amit. And but the ideas have developed since. And the question. The question that Daniel Amit and Stefano Fusi and later Larry Abbott were asking is, can we say something about the capacity, the memory capacity, assuming that synapses are slightly more biological? And the idea is to assume that synapses are bounded. So there are various ways of defining bounded. So the way that they were thinking about it is that the number of synapses has finite number of states, so they can change in a finite interval, and at some point they reach saturation. So the idea is that there is some saturation in synapses, and since synapses are biological entities, they saturate, there is noise, so the number of different distinct states of a synapse is finite. And many people, and the ideas that go back and forth in the literature, both the theoretical and experimental literature, and there are ideas about, or some people argue that synapses are in fact, or connections are in fact binary. Connections between neurons are binary. And a binary synapse would be an extreme example of a bounded synapse. A synapse that only has two states. But more generally, we can think about a synapse that has let's say m states. Now, so we have a synapse. Synapse has a finite number of states. Let's say that synapse can go from 0 to 1 in some units. So this would be 1 over m, this would be 2 over m, and so on. And now there is a new memory pattern. We present the animal a new memory pattern. So what can happen to the synapse? Well, three things can happen. Either just considering a single synapse. Let's consider this JJ. So three things can happen, right? Let's say that the synapse was here. So one possibility is that nothing will happen to this synapse. It will neither potentiate nor depress. Second possibility is that it will potentiate. And the third possibility is that it will depress. These are the three possibilities. And just for the sake of argument, we can, let's say that synapses can only move one step at a time. But this is not important. Number of states. So this is a discrete number. Let's say that m is 4. So this would be m plus 1 would be the number of states. So the synapse could be in a state 0, 1 over 4, 2 over 4, 3 over 4, or 1. Or m can be 56. I don't know what would be a reasonable number for a biological synapse, but a small number, much smaller than the number of neurons in the network. Now, in the Hopfield model, synapse could potentiate or depress as much as it wanted. Here we have an issue. So if a synapse doesn't change, then there's no information about the new memory pattern. So some synapses should change in order for memory to be maintained. Now, if a synapse is here, well, let's say that the synapse is here now. So let's say that the synapse is here, and a new memory pattern arrived, and it is supposed to potentiate. Well, it cannot potentiate because it is in saturation level. Then the synapse, well, depending on how exactly we model it, but let's say that the synapse does not change as a result of this potentiation, then we lose this memory. In some sense, we lose this memory. And also we lose some of the history that led to this state. Or we lose some of the history that led to that state. Now, if there are many memory patterns, at some point we will reach saturation, so we will lose information about things that happened in the past. So just for the sake of demonstration, let's say that we start from this point and we now find ourselves here. Now we don't know whether we find ourselves here because there were 100 potentiations, but still we only saw 2 of them and got stuck here. Or maybe we are here because there were, I don't know, 96 depressions and then 4 potentiations. They will both lead to the same point. So we lose information as a result of the saturation. And the question is, how much should we worry about this loss of information due to saturation? And it will turn out that this is a serious issue. Someone had a question here? So, a necessary condition, not sufficient, but a necessary condition for a memory, for something about the memory to be maintained, is that there will be information in the synapses about the potentiation and depression. So let's consider what I'll call, I don't know, a synaptic signal. So I'll denote the synaptic signal by S. And S will be a measure of the amount, a rough measure of the amount of information that there is in the network about a particular memory pattern. So the way to think about it is the following. So after a very long time, after many memory patterns were encoded in the network, some synapses are more potentiated, some synapses are more depressed. But we can talk about the average synaptic efficacy in the network. So there is an average synaptic efficacy in the network due to the fact that some were potentiated and some were depressed. Now we add another memory pattern. Some of the synapses now will be potentiated, and some of the synapses will be depressed. So I'm going to look at a signal which is average over all synapses in the network. I'm going to look at all synapses that were potentiated due to this particular memory pattern, and I want to see, this would be, I'll use the index I, and I want to see how different they are from the average. Only those synapses that were potentiated. And I'm going to look at the synapses that were depressed, and I want to see how different they are from this average. Now we expect that, synapses that were potentiated would be larger than the average, on average, and synapses that were depressed on average, or the sum over them, would be smaller than the average, and the difference is expected to be a positive number. That's, I guess, rather trivial. Now, so we take these synapses, and now we add more. We continue adding more memories, and we keep on looking at this signal, the difference between the overall weights of those potentiated and the overall weights of those that were depressed. Now, if this difference goes to 0, this implies that all information is lost about this memory, because those that were potentiated are no longer different from those that were depressed as a result of this memory pattern. So a necessary condition for a memory to be maintained, again, necessary, not sufficient, necessary, is that this signal will be positive. This signal becomes indistinguishable from 0 then we can say with certainty that the memory was lost. Questions? Yes.
What is the actual meaning if it will be negative? Can it be negative?
Well, it can be negative eventually, yes. But so let's say that rather than taking those synapses that were potentiated and depressed, I'm taking a random random number of synapses and I call them potentiated, and a random number of synapses and I call them depressed. It has nothing to do with any pattern that were presented. Now, this number is a stochastic variable, which depends on the realization of all memory patterns. It can be either positive or negative. We expect it to have a zero mean, and there will be some distribution depending on the size of these groups. In this framework, sometimes this S can be negative. We don't expect it to be more negative than expected by chance. Chance being just choose randomly from these two groups. Unless there is structure in the patterns, like temporal structure in the patterns. But assuming that memories are independent, then this term should be normally distributed. If we just choose random groups, and if we choose a group that is that was really potentiated and depressed, then this should be, at least for some time, it should be positive. Now the question, how many patterns can we induce here such that this will remain significantly different from zero? This is the question.
But if this term is negative, then
Which term? This is negative, this is positive. So the difference is positive. It's expected.
He talked about the
Yeah.
the whole thing.
Yeah. The whole thing is expected. Well, again, if we just take random groups, then there is a distribution around zero of this random group. Now, let's say that I wonder whether a particular memory pattern was encoded in the. Okay. So I'm doing choosing you. I do a surgery. I want to know whether you remember something from this class. Okay. I'm doing it not today, but 2 days from now. So the way that I'm going to do it is I know that a particular memory was supposed. I don't remember whether you were in class or not. I know that if you were in class, then some neurons, a particular subgroup of neurons, of synapses was potentiated, and a particular subgroup of synapses was depressed. I know which particular, because I know the pattern. I know what pattern I generated in your brain. Okay, so the way that I'm going to ask, the way that I'm going to check whether you were in class or not is I'm going to look at all those synapses that were supposed to be potentiated. I'm looking how different what the average value relative to what's expected from steady state, and I'm going to compare it to those that were depressed. Now, I know that by chance I expect some distribution. Now, if you're going to fall here, then I know that you were in class. But if you fall here or here or here or here, I don't know. Well, it could be that you were in class and you already, and everything is forgotten. But if you remember things, then you're supposed to be beyond this distribution. And again, if I want to be 5% confident, then I will put this threshold. If I want to be 1% confident, I'll put this threshold, and so on. But this is the idea. Now, the question that we are going to ask is, what happens to signals like this in the learning process? Now, we expect that as we add more memories, let's say that we start from this point, as we add more memories, then this term would move towards zero. And the question that one can ask is, how many memory patterns can we add until we reach this region in which there will not be a statistically significant difference between this term and this distribution? So this is a question. Am I clear? Yes.
The first term is on all the synapses that I know should potentiate for the given array pattern.
Yes.
And the second one another term, so it should be
The second one is for all those that were supposed to be depressed. Yes.
So why is the same index like
It's an index. I can because I can use a different index. It's not the same synapses, of course.
Okay.
Yeah. It's the same. It's a different group of synapses. It could be, for example, in the Hopfield model, all synapses are either potentiated or depressed. In other models, you can imagine that you randomly choose only 10% of the synapses to potentiate, or you randomly choose 10% of the synapses to depress. Okay? So how are we going to address this question? So as I told you, the one motivation for introducing this paper is to teach you a new technique and a new topic, and this topic is called Markov Chains. So now that we have a detour on Markov Chains, I'm only going to talk about first order, and this is a detour. So we forget about this synapses problem, and now we are going to focus on a completely different problem, or what seems to be a different problem. So let's assume that I'm going to draw my house, okay? My house has 4 rooms in it. So I have 4 rooms in my house. I will denote this by A, B, C, and D. So this is my house. And as you all know, so one thing to note that I can move from room A to room B, I can move from room A to room C, but I cannot move from room A to room D. I can move from room D to room C, but not from D to B. So there's a structure in my house. And every evening I drink, and then I start walking in the house, rather randomly. There is a structure though. So if I'm in room A, for example, there is some probability that I will move to room B, and there is some probability that I'll move to room C, but I will never move directly to room D, because I cannot, there's no door. So I can write the probability of moving from room A to room A is 0. So I'm on the move. Okay, I have to do something. There is a probability of moving from room A to room B, which is half. In this example, there's a probability of moving from room A to room C, which is also half, and the probability of moving from room A to room D is equal to 0. And we can also talk, for example, about probability of moving from B to A, which would be half, and probability of moving from B to B, which is 0, and there is a probability of moving from C to A, which is a third, and so there are rules that determine the transitions that I make. And the type of questions that we will be interested in are questions like, okay, let's say that I start the evening in room A. Where will I be after 10 time steps or 100 time steps. Now, you will not be able to give me a deterministic answer because the dynamics are stochastic. But you will be able to tell me, or hopefully, you will be able to tell me what's a distribution over the rooms that in which I will be, where I will be distributed in my house. So this is a kind of question. Now, I told you to forget about this problem, but thinking about it, it has a similar structure or a similar flavor. So I have a synapse in a particular state. Let's say that I'm here. And I'd like to know, and there are memory patterns that are added to it. So sometimes it's potentiated, sometimes it is depressed. So if there is a memory of where the synapse was, if such a memory is maintained, then maybe we can retrieve the memory trace. Similarly, if after 10 steps you can with some confidence be able to tell me that I started from room A rather than from room B, then there is information about the past. In a somewhat similar way to information in the synapse. So if we know how to solve this problem, maybe we'll be able to solve this problem. So this is a mapping between these two problems. Questions? So one way of describing this problem is using these transition probabilities. Another is by using a graph. So there are 4 states here, A, B, C, and D. And we can talk about the transition probability from A to B, which is half, and transition probability from B to A, which is also half. And we have B to C, which is a third. And we have D to C. The probability of transition from D to C would be 1. And there will be transition probability from A to C, and from C to A, and from C to B, and from C to D. So that's an alternative formulation of a problem. And again, the type of question that we're interested in is, given that I know where I started, where will I be after 5 steps, time steps, or 100 time steps? Will there be information about the past? Will there not be information about the past? Okay, so how are we going to address this problem? So why is it called? Well, I don't know. I can't give you the history, but the idea in Markov chains is that if I know the state. The idea in first order Markov chain, if I know the state of the network or the state of the world in one time point, then let me write it in a formal way. So the probability in time t plus 1, in general, or in a general problem, this probability can depend on the state of the world in time t, state of the world in time t minus 1, until, I don't know, state of the world in time minus infinity. So in general, you can think that There are systems that have long memory. I don't know. You're in a relationship and your spouse tells you, 5 years ago you said that I am... So this would be an example where something that happened 5 years ago has an immediate effect and you were not expecting it. Okay? But in Markov, in the Markov chains, first order Markov chains, the probability distribution on the state at time t plus 1 will only depend on the previous state. So if you know the state of affairs in the previous time point, you don't need to know anything about the history. So thinking about where will I be in the next time step, if I know that in the previous time step I was in room C, then I don't care where I was 3 time steps ago. So this is an example of, this is a first order Markov. First order Markov chain. Now thinking about this problem, so what's the probability? What will be the probability of being in state A at time t is equal to 1 as a function of the previous time point? So what are the options? I could have been, one possibility that in the previous time point I was in state A, and if I was in state A, so the probability of being in state A at time t is equal to 1 is equal to the probability of being in state A in the previous time point times the probability of transition from A to A. That's one possibility. In this case, it will be 0. Another possibility that in the previous time point I was in state B, and I moved to state A from state B. A third possibility for being in state A, that I was previously in state C, and I moved from state C to state A. And this will happen with the probability of transition from C to A. And the fourth possibility is that previously I was in state D, and now I moved from state D to state A. So this is the probability of being in state A at time t equal to 1 as a function of where I was in the previous time point. Now we can write, we can do the same thing for state B, state C, and state D. And the easiest way of writing it is using matrix notation. It's just to say that the probability to be in state A, B, C, or D at time t is equal to 1 is equal to the transition matrix, the probability of moving from A to A, B to A, C to A, D to A, and so on. This would be D to A, this would be D to D, and this would be A to D, and we have everything in between, times the probability to be in state A, B, C, and D at time t is equal to 0. Or we can say that P at time t is equal to 1 is equal to some matrix times P at time t is equal to 0, where in this case we can use these probabilities to explicitly write the matrix. So what will be the diagonal of the matrix? 0, because in this model I never stay in one state, and I'll just, to save time, I will just fill it. So we have half, third, 0, and then we have half, 0, third, 0, half, 0, 1, and 0, 0, third, and 0. So this is the matrix. So we know that P at time t is equal to 1 will be M times P at time equal to 0. And more generally, what will be the probability time 2? It will just be M squared, because probability at time t is equal to 2 will be M times the probability at time t1, and will be M squared the probability at time 0. So the probability at time t is equal to n will be just equal to M to the power of n P at time 0. Okay? So if we know this matrix M, and we can compute the powers of M, then we can answer all questions about this particular problem. So what can we say about this matrix M? Well, first, all elements in M have to be, can they be negative? No, they have to be non-negative. Why? Because these are probabilities. So we know that all Mij are non-negative, because these have to be probabilities. Do you have a question? Yes, and smaller than 1. But we can say something more than that they have to be smaller than 1. We can make a stronger statement. Each column is sum to 1. Why? Sum over I of Mi is equal to 1. Why? Well, because if I'm in a particular state, I can either move to B, C, and D, and the probability of moving to each of these different states, the sum of these probabilities, have to be have to be equal to 1, not 0. Sum over, this is true for all columns. So we have this matrix that determines the transition. Well, the details of the matrix will depend on the problem that we're studying, but we can say for sure several things. First, that all elements are non-negative, and that the sum of columns are equal to 1. Now, this matrix that has these properties is called, well, it has several names. It's called stochastic matrix, probability matrix, transition matrix, substitution matrix, or Markov matrix. All these are names given to this matrix. I typically use a transition matrix, but this matrix has many names. And soon we will talk about the properties of this matrix. Now, before that, I would like to go to this problem and discuss two types of Markov chains. So this is one type of Markov chain is drawn here, and this has the property that I can move from any state to any state after a finite number of steps. So if I'm here, I can move to D either by going A, B, C, D, or I can move to D by going A, C, D. But one can imagine different matrices that don't have this property. For example, you could imagine a different problem where these doors are always closed. So if I start in A, I will either be in A or B. And if I start in D, I will either be in D or C. So a Markov chain is called ergodic. A Markov chain is called ergodic if there exists n such that for all ij, the ijth element of m to the power of n, is larger than 0. Ergodic matrices are also known as irreducible matrices. That's just another name.